Welcome back. Having completed our lectures on nuclear fission, we will have a single lecture on nuclear fusion. Our discussion on nuclear fusion is rather brief because currently it doesn't have much engineering consequence. More, it has been studied more at a fundamental level. A practical nuclear fusion reactor is seems to be still uh, in the future. In any case, let's see where it is relevant and some features of nuclear fusion. So it is most relevant to understand uh, the energy production in sun. So and other stars. So typically, nuclear fusion involves uh, light elemental nuclei. The reason for this is the Coulomb barrier. When two nuclei have to come together to fuse, what is the main driving force or the main activation barrier against fusion is the Coulomb barrier, which is a strong electrostatic repulsion. So the Coulomb barrier and the electrostatic repulsion increases with atomic number. Therefore, uh, the Coulomb barrier favors fusion amongst light weight or low Z atomic nuclei. So that's why most of the fusion literature deals with light elements. For example, the Coulomb barrier uh, is of the order of, if it's of the order of zero point 0.7 MeV, this corresponds to a very high temperature. To overcome this Coulomb barrier, you need to have very high temperature. Remember, KT is 26 milli electron volts. So to overcome this Coulomb, this energy scale, the temperature needed is rather very high. So it occurs only in stars and sun, and so on. Okay. So this barrier is different from the barrier you saw in nuclear fission. Uh, so this is just purely due to Coulomb barrier. This is more long range compared to some of the things, activation barriers you saw in the case of nuclear fission. So to have such high temperatures, this is only possible if you have plasma state. There are two different cycles that are commonly discussed in the case of nuclear fusion. In one of the cycle, referred to as the carbon cycle, the first reaction is C12 reacting with the proton, forming a nitrogen isotope and energy. Then there is a series of reaction from here. So this nitrogen gives back C13 plus a positron. This reacts with the proton, forms N14 plus energy. These two are energy generating reaction, and so on. Eventually, what is important to notice is after going through this cycle, C12 gets generated again. This is what we start. One of the reacted was C12. That was generated again. So that's why it's called carbon cycle. You get back carbon, but you also get helium. So the overall reaction is the following: 4 proton gives you this nucleus plus 2 positron plus this much amount of energy. This energy is uh, significant, quite large, but if you look at the amount of energy you get per 1 meter cubed in the sun, the amount of energy output is rather less. That is because the number of fusion events in the sun is very less. Because even though energy per fusion event is high, the overall number of fusion event is very less because of the large Coulomb barrier. Therefore, the amount of energy which you get from 1 meter cubed of the volume of the sun is not that much. There is another cycle called the proton-proton chain. So here, the first step is 2 protons form a deuterium positron and energy. Then this deuterium reacts with proton, forms helium-3 plus energy. And these two helium-3 helium combine to give helium-4 plus 2 proton plus energy. So the overall reaction is, if you add all of them up, you get 4 proton gives you helium-4 plus 2 positron plus this much amount of energy. So both are look very similar. If you look at the overall reaction, it is just one of the same, except that how you get to this overall reaction is different. You get this by adding up all these reactions. You get this. You get this by adding up this reaction. So typically, which of the cycle predominates depends upon the temperature. At a lower temperature, proton-proton cycle dominates. At a higher temperature, carbon cycle dominates. If you look at the reasons, it will be if you look at the activation barrier or the Coulomb barrier here is quite different from the Coulomb barriers that exist here. So at low temperature, you typically have proton-proton cycle because you have lower Coulomb barriers. At a higher temperature, the Coulomb barrier can be overcome. So you have carbon cycle. So there are fusion has been a dream. A lot of money has gone into making nuclear fusion a reality, but it is still way into the future. So many different reactions have been considered for a practical fusion device. So these are some of the reactions that have been attempted. People are still attempting, but we're not anyway close to a success. One of the main reason is the Coulomb barrier. If you look at the cross section, that's what is plotted in the y-axis. This is in millibarns. As soon as the energy of the deuterium decreases. So, for example, curve A is this curve. It refers to deuterium tritium fusion reaction. As the deuterium energy decreases, the reaction cross section rapidly decreases. So this is a big bottleneck. Same thing is true for other reactions too. B refers to deuterium-deuterium reaction. C refers to D plus helium-3 and so on. Okay, so this is a big bottleneck. A very rapid decrease in cross section with a decrease in deuterium energy. So there is a criteria called Larson criteria. So what this criteria refers to is the energy output of the device should be more than the energy you put into the device. So there are certain main elements that go into determining whether you meet the Larson criteria. There are three main things. One is the plasma temperature, which in turn determines the plasma density. You want to have very high density to promote a lot of collision, and you want to confine it. If there is a lot of confinement, the chances of collision increases. Cold fusion, hot fusion even increases. If the plasma density is greater, again, hot fusion events increases. So these are the main determinants of whether you can meet the Larson criteria, wherein you want to get more energy out, more than what you put in. So that has been rarely achieved. There are two major approaches to fusion experiments on Earth towards a practical fusion device. So one is called the tokamak. So it was, I suppose, originated in Russia. So this uses magnetic confinement to confine the plasma and promote collisions. This is one of the major approach. This has given rise to a lot of fundamental studies on plasma physics. In fact, much of the books and fundamental studies of plasma physics have been done in the context of hot fusion. the approach. There's one approach, and then there's something called inertial confinement, where there's a huge consortia of many countries, including India, and much of these experiments, I think, occur in Europe. Okay, so here, lasers are utilized on a small region to see if we can get more energy out, more than what you get, more than what you put in. So again, this has been there's been only for a very small time you are able to successfully get more energy out compared to the energy fed into the system. So again, in terms of a practical fusion device, we are fairly it's far into the future. So that concludes our very brief discussion on hot fusion. Um, in the next topic we will take up is our very practical nuclear reactors. We will also provide nuclear reactors in the Indian context. So there'll be a series of lectures dealing with different aspects of nuclear reactors. Almost all these things depend upon nuclear fission. Thank you.